In the previous video, we looked at our first optimization, which was this regularizing section, where we implemented a windowed version, so it uses a specific iterator, the Windows iterator, to go over the whole array in an optimized fashion. In this video, we're going to use SIMD and see if we can speed it up even more. And just to remind ourselves, the naive update takes around 225 milliseconds in this particular benchmark we set up, and the windowed update is about a little bit more than twice as fast. So what I'm going to do now is read this section on SIMD acceleration, and then I will meet you back here and we'll talk about what the next steps are. Alright, so in our current algorithm, we're iterating over windows as is illustrated here. The red spot is the thing we're calculating the value for. And we're doing one value here, which depends on all the blue values. Then we move to the next one and the next one. So what we're going to do now is, instead of calculating one red value at a time, we calculate a multiple points at the same time using SIMD instructions. And then the iteration will kind of look like this. And that's pretty much the idea. Of course, the tricky part is all the details. So let's try to get started. I'll put it over here so we can reference it as we're writing. And I'm going to make a new file called, I don't really want to call it SIMD. Let's call it basic SIMD. And let's first of all put it up here, and I want to go into the library and add it here, basic. All right, great. So let's have, what did we call it in the other ones? Did we just call it update? We just call update. So let's have an update function here. And actually, let me go ahead and steal the signature like that. Probably we're going to need these things. I'm also going to copy those. And now I think we are ready to go. So the first thing is, let's do this so we can see a little bit more. The first thing is splitting up the input into the part that can be handled by this like a wider window, because it might not be that everything can be handled. We'll probably need to handle the edges later, but for now we'll just get all the parts that can be handled exactly. So the way to do that is to first calculate how many of the larger windows we can fit in. So we're going to need to know how big the SIMD instructions can be. And if you remember, I think we had something, not main probably, but here is an example of a SIMD function. And we can kind of use this macro to figure out how big the SIMD instructions are. For now, what we're going to do with size is just put it to 1, and later on we'll actually figure out what the CPU can support. Okay, so let's take a look at this code once I've typed it. So first we just look at the shape, then we try to figure out how many rows, sorry, this should be columns. How many columns can we handle with the SIMD instructions? So first of all, we have the total number of columns minus 2. That's because we need to allow space for these neighboring values that it needs to look at. Then we divide that by the SIMD. So basically, how many red squares do we have? That's how many we can fit in. Since these are integers, this is kind of like integer division. So it's only how many can exactly fit in there. And then we multiply by SIMD to get the actual number of columns. So for example, if we had 4, like let's say, or let's just take this example. We have 8, so minus 2 is 6. 6 divided by 2, because we have 2 red squares, would be 3. And then we multiply by 2 again to get 6. And you can see that how many columns does it touch when we kind of iterate over everything? It's 6. So that kind of makes sense. All right, so then we need this guy, slice macro. So here we're constructing a slice that just covers all of the things we can handle with CMD. So again, we start from 1, not 0, and we end not at the very end, but 1 before, because we have this like a little bit of a buffer zone around like this is to fit in the window. All right. Then we just take references basically to that part of the arrays. And now we construct the corresponding slice in the input. Here we need a little bit more, because here we're actually going to be iterating over the windows. We were going to be using the window iterator over the input. So there we need to include the parts of the window that we need. Regular input, and this is B and B. All right, so there we have that. Now we can then iterate over rows of the output arrays and the corresponding windows of 3 consecutive input rows in the input arrays. Great. So let's add this access import, which specifies a specific access, and what we can use that to, or what we need to use that for, is to tell ND array how to iterate over how to construct the windows that we need. So here we see it in Windows, regular in new access windows. So this method traverses over all windows of a given length along an axis. So here we want to iterate over the first axis, that is the rows. The size is 3, because we have 3 here. So basically what we're doing now is this iteration. You can see here we're taking all of this, forget that there's red or whatever, but we're taking like the whole 3 by whatever length, and that's what we're doing here, and iterating, returning an iterator over those wide windows, you can say. So let's turn that into an iterator. Then we zip it with V, because we need both the classes, both the different iterations. All right, and then we can do the iteration. Finally, we can do the iteration. When V. Okay, so we just zip them up, and that gives us all of that. So now we're just iterating over the rows. Now we should, within a row, we should iterate over the columns basically. But here I think we're going to actually be using the SIMD. So let's see. We have the out chunks. Split that into chunks like that. Zip that with the row. There's a lot of zipping. And deal with. There we go. And again, remember this window U is kind of like a wide row. So we create a new window here. And the width is the SIMD width. Number of red squares we want to process, +2, one on each side. And again, we need to zip that with the same thing, but for V. All right. Great. So now we have that, and now we can. So what does this do? It creates little windows, pretty wide windows. So that creates these guys, and that's also what we have here. Here we have some kind of crazy type, but basically it creates chunks. So this is kind of like, well, we'll see now, but it's kind of like a slice of multiple values. So U, V. So now we can see here the, oh sorry, not rows, but chunks. So I guess I should go down here. Okay. And great. So now this chunk is like a tiny array of size and D width. Because we cannot really see that from the type, but we know because that's how we create it. All right. So now we need some extra imports. We already have, thought we had float. No, it's from UV, I think. We put it into UV for some reason. Actually, let me put it up here. And then we need sky. Great. So then we want to extract the SMD input. We use the slice macro again. SMD width plus stencil offset. All right. So this one selects the center row, and this one selects the it's kind of weird actually. This one just selects one point, and this one selects a range going from the center to with SIMD width to the right. So it would basically select all the red squares, because we have here, okay, you go one down, you go to the center of the stencil, then you go to the center of the stencil, you go, and then you go SIMD width over. All right. So U is window U, slice input. Go. So it creates this type alias. Fair enough. Okay, so this is like a SIMD vector type. That's very interesting. So that's something where the compiler knows, or it generates instructions that loads it into the SIMD register. So we do this. Right, so here we are creating another window iterator over the existing windows, and these were the very wide windows. Now we're just iterating it's kind of funny. So this is like a it's kind of weird. I don't really get that. So we have these chunks which contain everything we need. Now we are creating another window iterator. So this one, window U, would be this whole thing. Now we're creating a 1 height but same d width, so it would be like 2. So it's kind of like iterating over this in blocks of 1 by 2. Okay. Just assume it's correct. So obviously this is something that would take a little bit of thinking if you had to design it yourself, at least for me. So we are, it's kind of funny because this is just a 3 by 3. And so what happens when you zip things that don't have the same size? 2 over the iterators, returning 2 over the first. If the zipped iterator has no more elements to return, then each further attempt to advance it will first try to advance the first iterator. First try to advance the first at most one time if it still yielded an item. All right. Let me type this out. And well, okay, we can talk through it. While I'm doing it, it's a little bit difficult sometimes to type and talk. But basically here we're zipping everything up, and then we are doing a fold. So we are calculating some single item from each from iterating over that full window. And basically this should be exactly the same as what we had before, but just CMDified. And want to return this. All right. And it should just be right. All right. What is this? Stencil V is a CMD, but V is just an array. So where did I get V from? What is U? That is SMD. Ah, it's because here I called it V. All right. So we're kind of iterating over the windows in steps of whatever. And then we are okay, so now I see here we get a full window, and then we are just getting one single number and with, okay, that makes a little bit more sense. So basically we get like U1, U2, U3, 3, we get a single number weight, but these we want to process in parallel by doing this, like this operation that we also saw before, to create the full U, full V, but basically the update values. So what we're doing here is we are copying or like repeating this value W, the weight, and then we're using these SIMD we're using these SIMD types. So basically, we are multiplying multiple numbers at the same time. All right, so far so good. So far so good. Now we have a bunch of stuff here. This is basically the same as before. So what I'm going to do is copy it. All right, so we have here, again, we're turning everything into SIMD vectors, so we can process multiple things at a single time. And here the out U is the final SIMD value, which we want to copy into the chunk from which it came. Here we have the chunks, or rather, here we have the chunks. All right. So first of all, let's check that this even compiles. It did seem to compile. And that's good. So what we need now is to not use a SIMD width of 1. That's a bit silly. Probably will be way slower. So let's go into the library and remind ourselves how we did this. So I'm going to chuck this thing on, and then I'm going to say that this is actually the SIMD width. Let's run check again. So this time it didn't compile because we don't have selected target, and we need to import those things. So we're compiling again, great. And I don't think we needed anything else. All right, so let's see in the exercise. Make a backup of your current update function, blah, blah, we always do that. Then integrate the above. So we did that, completed by adding function multiversion. We just did that. Finally, make your update function handle the regular part of simulation domain by reusing your formal implementation. Great, so that's the last thing we need. And I think actually, one thing maybe we can do is just call this one directly, but well, it takes this UV struct, so we cannot actually call it directly. But there might be some idea in factoring this out, so it only depends on these arrays. So maybe let's start by doing that. So here we have a public function, update, let's call it implementation. We still need some options, and then we need start U, which is, that should just be an array2 view of float, whatever that is. Oh, array view 2, I don't remember exactly, but that kind of stuff. So let me put that in here, and let me say use array view 2, and we also need array view mutable 2, and delete it. All right, so this is array view 2. We need the float. Great. So then we need start B, and we need, that's again an array view 2 float. We need end U, which is now immutable. Array view mute 2 of float. And find the end V, which is again an array view 2 of float. Great. So the shape here, I think this function just calls into U anyway. So actually let's make sure we do it like this. So shape is this thing. This is just start U. So now it's exactly the same. Okay, so we need this to be end and start underscore instead. And basically I think that's it. So it is complaining about something in this scope because I did that. Okay. Great. These guys, we need to refer to that. Cannot mutate. Okay, we cannot mutate, but I said it's mutable. So I don't understand that, but whatever. So that should do it. And now over here we can say use create naive update. So here we are only handling this. So let's say the irregular output. It's kind of difficult to make a slice for that because it's obviously it's the first one, and maybe I can do like this, so it's still a 2D array, and then it is all of the columns. So that would be one part, and then there's some other parts as well. So that's part 1, and this is like part 2. That, and we actually also have to handle like, and let's do it like this, number of rows -1, the first column and the last column. So that's gonna be right here. It shouldn't be that, it should be this, I think. Make it like that. All right. Okay. Like this. And here, what do we do here? We say number of columns -1. So all of these things we want to, and what we want to handle. So what is the corresponding input slice? That's a very good question. I think we need one more. Do we? Because we need the window. Maybe this is a silly way to do it, trying to call this function, because it will work over the full window and we don't really need that. So I think I'll think about a different way to do it, and then I'll be right back. All right, so what I decided to do is to take the same approach that we had in the windowed windowed update function, where we had this handle edge function. So basically copied that and adjusted it a little bit. Now the output the output, the ranges is like pretty much the same for upper, lower, and left, but the right one we handle differently, because if you look here, what we're doing is we're going up to the number of regular columns. So actually what we need here is this. So what we want to do is we want to start at the next one when we're on the right side, and then go up to the end. And then it's pretty much the same. So of course we should have this test that actually match the naive update. And here it's not going to be windowed, it's going to be basic. And this one we don't. It's basics in D. So actually let's run that. Basics in D. And it failed. But that's why it's good to have a test. That's why it's good to have a test. And let me... So it is one of these cases that fails. So let me try to debug that and I will get right back to you. All right, so the issue was that when we're iterating over these slices, the indices are kind of wrong. They are the indices within the slice, but obviously we want the index within the array itself. So when, for example, we're iterating over the right slice, we actually have to add something because index 0 is not the first column, it's actually the column at the way to the right. So I've included those like numbers here and just add them here. So now when we run the test, it passes, as you can see. All the tests being passed. All right, so basically now we have a CMD version. You know what the next step is? It is benchmark. Basic CMD and basic CMD updates. Go basic CMD. And let's go ahead and run that benchmark. And I will see you once it's done. Here we go. Let's see. So we have, everything went a little bit slower now. I don't know why, but whatever. So the naive update is still around 200 milliseconds. It was 225 before, but now it's 242, whatever. This one is again like over 2 times faster than the naive update. Then we have the basic CMD update, which is another factor of 2. So that's pretty cool. Of course, the code is kind of getting quite complicated. You have to really... It's hard to read this. I mean, there's no way of getting around that. But I think if you draw these kind of diagrams for yourself like this, maybe it can be a little bit easier to understand. All right, that's going to do it for this video. Next time, it's apparently time for advanced CMD, whatever that means. But we'll see that in the next video. Until then, bye-bye.